This is part one of a three-part lecture, which is based upon a presentation I gave a few years ago to the United States Coaching Association meeting. And you may not be aware, but each of the governing bodies in U.S. sports has a scientific branch. And to be a coach requires that you attend workshops on coaching and physiology and other aspects of preparing youth and others for sport performance. So this is what was given to 800 meter, 1500 meter middle distance coaches. And for you, it should be in large part a review, but it's a different way of looking at what we've been talking about, the energy systems we've been talking about. I presented to the coaches what anaerobic capacity is, and that's what this part one is, an overview of energy production in exercise. And then we specifically talked about the importance of the anaerobic capacity, and then how to measure it. And of course, all the questions they had were how to improve it. Muscles use energy to produce force. Energy is in the form of ATP, adenosine triphosphate. We have very small amounts of ATP stored in the muscles, so we must maintain or replace or replenish these stores, and we do that using the aerobic systems, which involve the utilization of oxygen, and anaerobic systems, which do not require oxygen. I'll give you just a moment to look at this. It's aerobic oxidative phosphorylation, and you'll see that there are the three different fuels shown: carbohydrates at the top, fats on your left, amino acids on your right. So just take a second to look at this and make sure it looks familiar, and then I'll talk about it briefly. All right, going from top to bottom, you see carbohydrates, glucose, being converted to pyruvic acid, thence to acetyl-CoA, which enters the mitochondrion. So this is Embden-Meyerhof, the first part. Conversion of pyruvate or pyruvic acid to acetyl-CoA. And then part 3 in the mitochondrion, the Krebs cycle or the tricarboxylic acid cycle. And part 4, electron transport system. You can see that using glucose for fuel, we get 2 ATPs produced up in Embden-Meyerhof, and then 34 ATPs produced through the activities in the Krebs cycle and the electron transport system. And also you can see that oxygen is required and carbon dioxide is produced. To your left, you see how fats can also be utilized for fuel aerobically. Through beta oxidation, fats are converted into lots of acetyl-CoA. And similarly on the right, now for the coaches, I just showed them that amino acids from proteins can be converted to acetyl-CoA. You know that some amino acids are converted to acetyl-CoA, some are converted to pyruvic acid and thence to acetyl-CoA, and others, through other pathways, directly enter the mitochondrion. But for the coaches, it was enough to show them this, that fats, carbohydrates, and protein in the form of amino acids can all be used for fuel aerobically. Then we discussed what are the advantages of this system. High capacity. You can produce energy aerobically until you run out of glucose. And that in our parlance is fats burn in the carbohydrate flame, so you can keep going as long as you've got carbohydrate. So high capacity. It's efficient, meaning you get lots of ATP from one glucose. And this is rather descriptive and rather broad, Maximal rate of ATP production aerobically can be sustained for about 7 minutes, and a submaximal rate can be sustained for about 2 hours. Now, the downside to this system is it's relatively slow to respond, and we would call that the kinetics. And it has a relatively low rate of ATP production. Okay, relatively low rate, well, it's all relative. If you're a highly trained endurance athlete, this submaximal rate that you can sustain for 2 hours, that you can sustain for a marathon, these highly elite people run sub 5-minute miles, 26 of them back to back. So if you consider a 5-minute mile a low rate of energy production, then yes, the aerobic system has a relatively low rate of ATP production. Now for the anaerobic energy production, and this is what my job was to teach these coaches, but I'm just hoping it'll help you see how all three systems work: aerobic, glycolysis, and phosphocreatine. Glycolysis, your carbohydrate, glycogen, glucose, is broken down to pyruvic acid, just as it was aerobically on the previous slide. And again, we call this the Embden-Meyerhof pathway, and there's your 2 ATPs being produced. Only in glycolysis, the pyruvic acid is then directly converted to lactic acid, and that is the overall pathway, glucose to lactic acid. And of course, you know, glucose yields 2 lactic acids plus 2 ATPs. Advantage of glycolysis, and whenever we give an advantage, we're usually comparing it to something else. So compared to aerobic energy production, glycolysis, the anaerobic breakdown of glucose, responds more quickly, that's its kinetics, and it produces ATP faster, that's its maximal rate. Now the capacity is somewhat limited, and it is determined by this effect of lactic acid and the acidity that it causes. The acidity, measured as a drop in pH, causes pain that we have talked about, causes reduced muscle contractility that we have talked about, and it reduces glucose catabolism, meaning the breakdown of glucose, meaning, if you look back onto the middle of the slide, that first arrow between glucose and pyruvic acid, that series of steps gets blocked. So if the pH gets low enough, glycolysis shuts down. That's a protective mechanism to keep you from producing more lactic acid, but it also keeps you from producing more pyruvic acid, which means when it shuts down glycolysis, it also shuts down the aerobic oxidative phosphorylation of glucose. And as you remember, when you shut down the aerobic oxidative phosphorylation of glucose, you also are shutting down aerobic oxidative phosphorylation of fats. So when the pH gets very low, every pathway we have, every pathway we've discussed so far, gets shut down. Now, what's the second anaerobic pathway? ATP-PC system. Very simple. It uses creatine phosphate for fuel, and there's the reaction, the summary reaction showing the transfer of the high-energy phosphate from the creatine phosphate to the adenosine diphosphate to produce ATP. You can see on this slide I'm using 2 abbreviations for creatine phosphate or phosphocreatine, and again, 2 abbreviations, exactly the same thing. Advantage of this system, kinetics and maximal rate. Disadvantage, an even smaller capacity than glycolysis. And like glycolysis, once the system is exhausted, in this case, once the creatine phosphate supplies are depleted, the game is over. So, to summarize, And again, this was summarizing for the coaches. The aerobic system is efficient, lots of ATP, it has a high capacity, it can use fats, carbohydrates, and protein for fuel. It does have slower kinetics, a relatively low maximal rate, and then I also discussed for them that the anaerobic threshold represents this sustainable rate. And again, that sustainable rate is something like a marathoner's pace, which is rather impressive. Then the second and third systems were the glycolysis and the phosphocreatine system. Glycolysis produces lactic acid, and it is therefore often referred to as the lactic system. Phosphocreatine does not produce lactic acid, so it's often called the alactic system. And I've highlighted in yellow the important characteristics of these systems, of these anaerobic systems: kinetics and power. They respond quickly, and they produce ATP at a high rate. And it is these characteristics of the anaerobic systems that make them so valuable in middle distance running and related activities. So this was an overview for the coaches and a review for you of ATP production via the aerobic and anaerobic pathways. I hope you remembered the important characteristics of the anaerobic pathways and our discussions about kinetics, power or maximal rate, capacity, and then this underlying but very important characteristic of these systems is that when they are exhausted, you are exhausted. Next time, in part 2 of this lecture, we'll discuss how these characteristics determine the role of the anaerobic pathways and the aerobic pathways in exercise.